So we mentioned previously this fact that if you've got a continuous map that's a bijection, then the inverse map in the opposite direction isn't necessarily continuous, and so your original map is not necessarily a homeomorphism. This is a kind of an irritating phenomenon which we'd really rather avoid. But we can there's a kind of nice theorem that we'll prove in this video which allows us to avoid that problem under certain additional conditions. So in order to make that work, we need a couple of results we proved earlier, but I'll just record them again now as a reminder. So the first result is like this. If X is compact and Y is a closed subset, then Y is also compact. Closed subspaces of compact spaces are compact. And secondly, if X is Hausdorff and Y is compact, then Y is closed. Okay, so fact A, I had a fairly simple proof. Fact B was a bit more elaborate, but I won't recall anything about the proofs just now. We'll just remember that these things are true. So now we can have this theorem. Let f from x to y be a continuous bijection where X is compact and Y is Hausdorff. Then the claim is that the inverse map is also continuous, and therefore F is a homeomorphism. Okay, so that's the main thing we're going to prove in this video. Okay, so we'll use the symbol G for the inverse of F. So we're claiming that so we want to claim that G is continuous. That's the key thing we're supposed to be proving. So that's what does that mean? It says that for any open U in X, the preimage G inverse U is open in Y. Okay, so that's kind of the definition. But equivalently, we can say that for any closed preimage of any closed set is closed. Okay, so yeah, remember this first thing about preimage of open sets open. That was our official definition of continuous, but it was a lemma that we proved quite soon after that, an easy lemma that it's equivalent to say that the pre-image of any closed set is closed. That's just because the closed sets are precisely the complements of open sets. The pre-image of the complements, same as the complement of the pre-image. So these two conditions are quite easily equivalent to each other. Okay, so so we've got some closed f and x right now, and we need to show that the pre-image is closed in y. As f is closed in the compact space x, the fact that we called A on the previous board, that says that y says that f is compact. Okay. So now we can consider f. This gives us a map from f to the image. So this is f is continuous, so it remains continuous if we restrict it like this, and it gives us a map from f to f of f, and just by the very definition of f, this map's surjective. So we've got a continuous surjection from f on to f of f. That proves that so this is a compact subset of y. Okay, because so that's another of these basic facts about compactness. Whenever you've got a continuous surjection from a compact space to some other space, then the target space also has to be compact. Okay, so now we can see that f of f is a compact subspace of y, and the hypothesis of our theorem is that y was supposed to be Hausdorff. Okay, so we have a compact subspace of Hausdorff. Therefore, f of f is closed in y. This was the fact B that we mentioned on the initial screen. Okay, any compact subspace of a Hausdorff space is automatically closed. And also G is inverse to f. So that means that the pre-image G inverse f is same as the image f of f. Okay, so and we just finished proving that f of f is closed. In other words, G inverse f is closed as required. So we've proved that under G, the pre-image of any closed set is closed, and as we mentioned, that's equivalent to G being continuous. And so G is f was continuous by assumption. The inverse of f is G, which is also continuous by this argument we've just given. F and its inverse are both continuous. That means that f is a homeomorphism. So now we'll explain a sort of typical application of the theorem that we just proved. So let's define x tilde to be set of x, y, z in R3. So we're going to assume x squared plus y squared is less than or equal to 1, so we're within a distance 1 of the z-axis, and z is plus or minus 1. Okay, so this is a union of two disks. You've got your top disk here at height 1 and your bottom disk here at height minus 1. Okay, and that's our x tilde. And x is going to be quotient space Okay, so what we're going to do is we're going to take these two discs and we're going to glue the two edges together. So if we want to be a bit more formal about it, what we're saying is that x, y, z is going to be equivalent to x prime, y prime, z prime. In there's two cases. Well, firstly, it's got to be an equivalence relation, so everything's got to be related to itself. So we have to include in our definition that things are equivalent if they're the same. And then the kind of interesting bit is that if you've got kind of the same point on the boundary, except one's in the top and the other's in the bottom, then they get identified together. Okay, so that's our thing. Okay, and then we define a map F naught from this x tilde to the unit sphere S2. Okay. By kind of squashing the top disk into the top hemisphere and the bottom disk into the bottom hemisphere. So that's F naught x, y, z is going to be x, y, and then we're going to put in a root 1 minus x squared minus y squared to ensure that we're on the sphere, and then we're going to multiply by z, which is plus or minus 1, so that won't change the square of this. That's going to put us on the sphere. So this is E saturated. In other words, it sends equivalent points to equivalent points. I mean, why is that? I mean, if you've got a point here and the corresponding point there, so these are kind of on the boundary, so x squared plus y squared is equal to 1. So in the second factor here, your root 1 minus x squared minus y squared is 0, so it doesn't matter whether z is plus or minus. So these 2 points here and here, they get sent to the same place in S2. They just get sent to the obvious kind of equatorial point between those things. Okay, so so that's an E-saturated map. Induces a map F from the quotient space X, which was X tilde mod E, to S2, which is so this is going to be continuous by this was kind of by the key property of the quotient topology. Okay, so so this was the basic proposition we proved about the quotient topology, that if you've got a continuous E-saturated map, then the induced map out of the quotient space is still continuous. I won't go through the details, but it's kind of easily seen to be bijective. Okay, so we really want to prove that that F is actually a homeomorphism, but it would really quite fiddly to do that sort of directly by considering continuity of the inverse. But we can do it sort of automatically from the theorem that we just proved. So here x tilde is bounded and closed. Therefore compact. Okay. And we proved a fairly easy argument a little while ago that the any quotient of a compact space is also compact. And and S2 is a metric space. So it's a metric space, so it's Hausdorff. And so we've got a continuous bijection from a compact space to a Hausdorff space. So F is a homeomorphism by the theorem that we just proved. So that's a fairly typical application of that theorem. You've got a map from a quotient space into some subspace of Rn or something like that. The subspace of Rn is metric and therefore it's Hausdorff. You've got a quotient space. Typically it's easy enough to prove that quotient spaces are compact in the case that they are. So it's typically fairly easy to show that your source is compact, your target is Hausdorff, and so if you've got a continuous bijection, continuous bijection, then the theorem tells you that it's actually a homeomorphism.